It is going to work. All right, so I remind you, this was something we saw last time. Um, you have the current source, so you can predict, you can figure out what's going to be the base voltage, try and measure it. Then what would be IE, which is basically the same as IC, right? The simple picture. And then vary our load from one extreme to the other and try to explain what you see using the two rules and the other ways of using beta down below, right? Then you're going to be constructing this common emitter amplifier. And so it has a bias network, so you should notice that. You could, whatever two, you may not be able to find. I think 130 and 150 should be available. In any event, you should calculate what the base voltage is and verify it. And then he tells you there the 1 microfarad. So that has to do with the input Z that's created by the bias network, and of course the transistor itself. And you know something about that from 4W1 and 4W2, which we'll go over on Tuesday. Right now, the idea is just to calculate it, measure it. So write it in your logbook, of course, so you see it, and then take note that now you don't have a negative power supply, but you can put a V in that goes negative. And you should explore what's the limits, like how much amplitude. And if you can't produce enough amplitude, you can always use the offset button to explore the limits. Sir? What's the voltage at the base? And if you get exactly, and in fact, this was assuming 15 volts, right? So you have to do the calculation with 12 volts because that's the size of your power supply, right? So you can calculate that. Then you know what is VE, and in principle, that should be the center of your output. So you should check and verify that, right? I don't know if I was that absolutely clear on Tuesday. So you should oops, trying to do too many things at once. So you should calculate. Okay, come on. Draw menu. All right. So you should calculate V bias, which is also V base in this case. Measure it. Then you can say what is VE, and how does it manifest in the output? In V out. And essentially, it's going to move the center point up. You also have limits to how high you can go and how low you can go. So I don't believe you can go all the way down to 0 because you have to deal with diode drops, and you have to remember the two rules. You have to always satisfy the two rules that VCE is a few tenths of a volt and that V base has to be able to be 0.4 volts to 0.6 volts lower. VE has to be able to be a little bit lower than V base. And well, more than a little. VCE is a few tenths. VBE is several tenths, like big 0.6 to 0.4. In fact, that's tenths of a volt. Okay. And of course, and how close to 0 is basically how far negative of an input and how far positive of an input can you reproduce? Then, oh, there it is. You have a quiescent current you can calculate, and in fact, should we I'm not sure if he even asks you to. He might ask you to directly. Is you can measure V out and V in. You know how to do that now. And let's double check to see what he asks you to do. The things I wrote up there, I know that he didn't explicitly ask you to do. That's why I wrote them there. Okay. Right. He actually does want you. No, wait a minute. I'm looking at the example. Sorry. Common emitter. Yeah. So it asks what should the output impedance be, and it says try to measure it. Right. You can do the same with the input impedance. What's its low frequency 3 dB point? That means you pick a certain capacitor. You can measure the 3 dB point, and that'll give you a clue because it's it's an RC constant, but you have a 56K and a 5.6K. You don't even have a resistor to the base. So how would you check and see what's its 3 dB point? And you know that you can and look it for a phase shift, for example. All right, let's try in case it. Oh, all right, the next one. Oh, and also you can check its gain. The gain is R collector over R emitter. See if it comes out the same way. And that's your V out over V in. So R collector over RE should equal V out over V in. See if it's true. This looks like a gain of 100. So he just says check its output impedance. No, input. I put it up there. Input and output impedance. Okay, so that you would put a resistor between the 0.33 microfarad capacitor. So your test resistor would go in here. It actually doesn't matter. You could put it on either side of the capacitor. And then for the output impedance, you're putting a load down here for Z out. And then this is for measuring Z in. All right. I'll post these. So then he says now add in this capacitor. And now he says input a triangle wave instead of a sine wave or a square wave. So I wondered about that. And, you put in a square wave because it gets you all the frequencies. A sine wave is a single frequency. And I looked up the Fourier transform of a triangle wave, and you can basically consider it to be like a sine wave in terms of It's essentially a pure frequency. There obviously has to be other ones in there. And the point is that you have to notice that the R emitter now is a combination of the capacitor and the 750 ohm. We also remember that a capacitor is a frequency-dependent resistor whose resistance goes down at higher frequencies. And it's in parallel with the 750, so that means the higher in frequency you go, then the lower is RE, so the gain should increase. And so armed with this little bit of information, you can calculate what is the Z, or simply what is the resistance of the capacitor at 1 over 2 pi 10 times 10 to the third times 15 times 10 to the minus 6. And so you should do that calculation. And what happens is you're going to make R emitter so small because, remember, once the resistance of the capacitor becomes 1/10 of the 750, we can ignore the 750. And you're going to calculate it, and you see these numbers here of 12 ohms, 25 ohms, and 50 ohms. I'll get back to those in a minute. What they come from is that it's our old friend, the diode turn on. So if you eliminate the emitter resistor and you're changing the BE, the voltage from base to emitter, as it increases, the diode turns on, and if you invert the plot, V and I, we know resistance equals V over I. So we can calculate an effective resistance, and it has to do with the Boltzmann constant and Bose-Einstein statistics. In fact, you're going to study that over the weekend with the reading assignment. So there's an effective little RE there. The thing that's hard to interpret is why does the barn roofing, which is, you should realize, is a loss of gain, why does it happen there at the top? And it's not a frequency effect about using a square wave or a sawtooth wave or a sine wave. The triangle wave is enough like a sine wave that you don't have to, it's not that effect. It's not a frequency effect. You can assume that the frequency is the same over the whole thing. And you'll also notice that this effective R is much larger than the R you're going to calculate with 1 over 2 pi FC. So basically what's happening is that the current is going to be determined because there's no emitter resistor. Well, effectively, it's going to be these resistances. And when and remember, this is, in this case, this is supposed to be held at a baseline of about 7.5 volts. So as you bring in the output up and up and up, the voltage difference between these two guys becomes less and less. And there's a diode drop, but basically it's this voltage down through no resistance. So you're basically, it's the voltage difference across the 7.5K resistor. So as your output goes up and up and up, the voltage drop across that 7.5K resistor goes down, down, down. I collector now is governed by that because there's no resistor down below other than the small amount of emitter resistor. And also the emitter resistor. And so that means then that the gain is going to suffer because that emitter resistance is higher at the lower current. It's hard to interpret. We'll repeat it next time. I just wanted to give you a flavor of it. For now, you're just expected to wire this up, look at V in versus V out, and sketch them, and the V in, the V out, you have this barn roofing, so called. And notice it tells you you have to attenuate the output because the gain gets killed pretty easily. So you have to use your 40 dB attenuation of your function generator. So some of them, like, you have to attenuate. And some of you have 20 dBs, some have 40 dBs. And it's a switch or a button to press on your function generator. You just ask me and I'll show you. Okay, so essentially the last part of the chapter is a transistor switch, which he'll say is kind of like lame. Why would you bother to do this? But what you should do is you can calculate what I base should be. And these big transistors have a beta of about 20. And you can actually measure the current here. And you can measure the resistance of the lamp. A lamp resistance changes when they turn on. But you can measure IC, and you're basically going to notice that it's not as big as beta times IB, even if beta is low as 20. And this is called, we're operating this thing in saturation, and I looked at, like, he wants you to explore, and it's not even quite clear how to do this. And we haven't really done it in class before, and I haven't really decided what is the use of it. I mean, I was taught transistors this way by Dr. Coleman many years ago, and that we actually, that big oscilloscope, is it back there? There's a big oscilloscope floating around on a cart, and it had a special attachment. I guess it's up in the 4700 lab. And you could actually plug in a transistor to it, and it would make this. It wouldn't do the red line, but it would, on an analog oscilloscope screen, it would produce all these lines. And it has to do with that turn-on business. And don't even bother writing this down because it may become useful when we study field effect transistors. But what happens is you when you decide on what transistor to use by using all like the gain, the beta, and things like that, and then you pick where you're supposed to operate it. But they don't. Hayes and the guys at Horowitz and Hill, they don't make a big deal of it. So we're just going to skip this part. So I have light bulbs. I have 10 light sockets. They're up on the windowsill. There's extra light bulbs. I would assume 10 should be enough because I doubt we'll all be doing it all at the same time. Oh, and you need to take your needle nose pliers and you need to grip, and I laid one of those things out here to show you, and of course it's not here. But these transistors are really burly. And if you can damage your breadboards. So you need to take the leads and grip them with your needle nose and twist them 90 degrees, because you're going to put them in across rows, and then they're rectangle shaped, and the contacts are actually rectangles. So, but the problem is they're oriented the wrong way. So you have to twist the leads 90 degrees. And if you're not sure, let me come and help you, because you'll damage the breadboard if you don't. And so set this up, and you can measure currents. And what basically happens is that even though you have the 470 ohm resistor, the current is basically determined by the load. But you should try and measure. You should figure out what is the base voltage. And in fact, it's not 5 volts over. That's a mistake, because remember, there'll be a drop across here. So it's no. Wait a minute. Yeah, will it be 5 volts? Well, figure it out. Measure, calculate it, and measure it. You know how to measure currents. Okay, and then the part that's interesting is this one, actually. And I can set up a demo of this too. That's kind of cool. So, and in fact, it's so dramatic. It talks about, and with 10 millihenries, with such a tiny inductance. Notice that he says you need to use a battery instead of your power supply. And so what you're going to observe is a monstrous spike. And in fact, you're going to attach your oscilloscope to watch this. And so you connect the battery and disconnect it, and you're going to see that it's 0. And let's see, where would you put the right, 2 scope? Duh. And you're going to notice this monster spike, and then it's going to settle out at 1.5 volts. And this has to do with the fact that as soon as an inductor sees a voltage, it instantly produces a reverse voltage of the same magnitude. In fact, if you do the math, it's infinite when you do the derivative. And in principle, it goes very high, but there's always a delay in the measuring and such. Let me think. Oh, okay. And then over there on the table, I have 5 batteries that I soldered wires onto them. The wires have a tendency to don't let them touch each other, or it's not a catastrophe, but it'll kill the batteries. And what stinks is I got a whole bunch of battery holders. I forgot them at home, so I had to solder wires on. All right, so then that would be there's a discussion at the end of the chapter about noise on the power supply, and call me over when you reach that point, and it walks you through trying to see if it's from a radio station or if it's from your power supply. And the technique is that if you have your plus 12 volts, and let's say it's supplying voltage to something, and you just put a capacitor to ground. And so typically it's zero point 0.1 to 1 microfarad. So that's what he's asking you to do, is to add, that's called a bypass capacitor. It knocks out high frequency elements because the resistance to high, and you want the DC to pass. All right, so then for reading assignment and notes, it's chapter 5N, and let me make sure how far we want to go. Transistors 2. Yeah, 5N, 5.N.1 to 5.N.4, up to temperature instability. It's talking about just what I gave you a little taste of it with the little r sub e. And there's some intimidating. If you haven't taken thermodynamics yet, it might be a little intimidating, but it boils down to a very simple equation. Well, you'll see it. And then he also goes into more details about calculating the input and output impedance of the phase splitter, which is something you looked at over last weekend and took some notes. And we haven't. You guys are at this. I wanted you to see if you can get through chapter 4 today, and on Tuesday we'll start out by talking about the 2 worked examples and the reading assignment of chapter 5. Okay, time to stop. Get to work.